Okay, thanks. As usual, I'd like to thank the organizers and the Institute and also all the participants. I really had fun so far. It's a great workshop, and the schedule, like a full-length talks, which we can really say meaningful things, and I was really inspired so far. So today I'm going to talk about the extension of the classical Matsuno-Gill model, which was originally developed on the infinite equatorial beta plane, to the sphere. And the key word in what I just said is the extension, because that defines some narrow sense of what we want to achieve. And also it justifies all sorts of choices that are otherwise unjustified. So, and thanks also to Vladimir for introducing already much of the material a couple of days ago. So when people ask me what is the Matsuno-Gill model, not that anyone does, but if they were to ask me, I would tell them the following three things, not necessarily in this order. From an atmosphere ocean dynamic perspective, it's the simple, if not the simplest description of the dominant circulation patterns in the tropics, namely the Hadley circulation, where there is equation to equator to pole, temperature difference with rising motions in the equator and subsiding motions in the subtropics. But most notably, the Matsuno-Gill model is studied in the context of the Walker circulation, where there are zonal asymmetries, such as the Pacific warm pole, where there is rising motions in the Western Pacific and sinking motions in the Eastern Pacific. But then in terms of a definition that we can really do something with, it's the steady state solutions of the force dissipated, linearized, rotating shallow water equations. So I take all of that to be the definition, including the linearized and rotating. And finally, from a physical intuition perspective, it's a driven harmonic oscillator in the atmosphere and ocean. And that perspective is a key to understand the contribution of this work, because you can imagine that the normal modes on the sphere are different from the ones on the beta plane. Right. So as I mentioned, it was originally introduced in the context of the infinite equatorial beta plane, or the shallow water, the steady state force dissipated shallow water equations on the infinite equatorial beta plane, which are shown here. We have the zonal momentum equation, meridional momentum equation, continuity equation, where u and x are the zonal and meridional coordinates, u and v are the corresponding velocities, phi, capital phi is the geopotential height, gamma is the dissipation term, and I'm going to say something about it in a second, and q is a prescribed forcing, meaning that it's a known function of the coordinates. And a key property of the system on the infinite equatorial beta plane is the fact that the free system, that is with a zero right-hand side with no dissipation and forcing, can be made parameter free. In contrast, this is the steady state force dissipated shallow water equations on the sphere. And aside from the spherical terms, the key difference is the fact that we can only reduce it to a single parameter, which is denoted here by epsilon, which is called Lamb number, and is equal to omega a squared over gh, where omega a and g are the angular frequency, gravitational acceleration, and mean radius, and h is the layer of the shallow water layer. And under this scaling, the Lamb number appears in front of the Coriolis term, so it plays the role of the non-dimensional rate of rotation. And a couple more words. First, there is a vast literature about the use of linear damping, and the key point is the fact that it's a sort of surrogate for nonlinear processes. There is debate on which nonlinear processes exactly, but it stands for nonlinear processes. And this is where I get to play the card of the extension, because Matsuno and Gill assume that the mechanical damping rate is equal to the thermal damping rate, which is unrealistic because, for one thing, the thermal damping rate has a double role. It plays the role of both dissipation and relaxation, so it can also add energy to the system. So it means that the rate of energy input is equal to the rate of the energy output in the system. So, to put it in Gill's word, the mathematics is simplest when the gamma for friction is the same as the one for cooling. Yeah.
So if you drop the
yeah.
is the model?
I have no idea.
Sorry?
Sorry? There are works where the mechanical and damping coefficients are different, but I'm not sure if there are works with no mechanical damping at all. Yeah, and more interestingly, yeah, absolutely. Another direction which people are starting to look at is to make the damping coefficients coordinate dependent, and then it right. Yeah, I mean, my life is simple because I mentioned I want to extend the Matsuno-Gill model, so I hedged this kind of questions. And the second thing I wanted to mention here is the fact that the coefficients in the equations are lambda independent, so we can do a Fourier decomposition and consider each Fourier mode independently. And it's a linear system again. So Matsuno solved the problem on the infinite equatorial beta plane with this forcing, where the zonal part of the forcing is indeed a single Fourier mode, and he solved it with respect to a periodic zonal domain. And the meridional part of the forcing was a Gaussian, which importantly corresponds to the geopotential height of a Kelvin wave solution of the free problem. And so this is the forcing Matsuno considered, and this is his response. And Gill solved a slightly different problem. The meridional part is again the geopotential height of the Kelvin wave, but in terms of the zonal component, he looked at a finitely supported forcing with respect to an infinite zonal domain. And a key property of Gill's analysis is the fact that he looked at the constituent waves. So the response consists of a eastward moving Kelvin wave and a westward propagating westward wave. Did I say Kelvin? Or a westward propagating Rossby wave. So this slide is actually counterproductive to the point I wanted to make, which is just how prevalent this model is in the literature. It was cited thousands of times, but it does show that how prevalent it is in the context of different phenomena, including the Madden-Julian oscillation, intertropical convergence zones, superrotation, monsoons, weak temperature gradient, even stratospheric chemistry, equatorial models in Joe and Vladimir's work, and also even Amazon deforestation indirectly via changes in the Walker circulation. So why do we want to extend the model to the surface of the sphere? Well, there exists large-scale long-term forcing on Earth, mostly in the upper and lower boundaries. So in the lower boundary, we have things like topography, ocean heat fluxes, and land-sea contrast, all of which have global scales. And also in the top of the atmosphere, we have radiative forcing. So for example, the incoming or the net incoming solar radiation is roughly, varies roughly as a cosine of the latitude, which has a global scale. Then the Lamb number, which depends on the static stability, varies by at least 4 orders of magnitude on Earth. So it's not like a single value. And likewise, the dissipation rate, which is very difficult to constrain by observation, varies by at least 1 order of magnitude. And this is the place also to mention that these two, there is ample evidence to suggest that these two also change under climate change. So it's additional motivation to consider a range of values. And finally, the validity of the beta plane approximation depends on Lamb number, which brings me to the next point, which is the fact that the free shallow water equation on the sphere has 2 solution regimes. There is a global solution regime where the solution covers a large fraction of the sphere, and an equatorial solution regime where the solutions are equatorially trapped. And roughly speaking, as you can see from this figure from Boyd and Zhao, for a fixed zonal wave number here on the ordinate, for a fixed zonal wave number, the global solution regime is realized at a small Lamb number, and the large equatorial, or the equatorial regime is realized at large Lamb number. So this is where we expect to find the beta plane approximation. And so in terms of extending the model, we want to make sure that the equations or the solutions on the sphere would converge to the beta plane solution in the appropriate limit, that is large Lamb number. And for that, we need to make sure that the forcing is also would also converge to the original forcing considered by Matsuno and Gill. And as I mentioned, the meridional part of the forcing, at least in the case of asymmetric forcing, was the geopotential height of a Kelvin wave. And Gill also considered an anti-symmetric forcing and a completely asymmetric forcing, which was the sum of the two. But anyway, we are going to use a forcing which is the extension of the Kelvin wave to the sphere, which ties back to earlier works we did of how to identify the Kelvin wave and also the MRG mode on the sphere. And this is essentially the sermon of our work. We have a 2-dimensional parameter space, and we are going to examine the Matsuno-Gill model or the solutions in this 2-dimensional parameter space. So the Lamb number is going to be on the ordinate and the damping on the abscissa. And we have 6 decades in each direction between 10 to the minus 3 to 10 to the 3. And we are also going to consider 9 particular samples corresponding to the combinations of light, moderate, heavy damping, and slow, moderate, and fast rotation, where the light and slow refer to parameter values equal 10 to the minus 2. Moderate is a case where the parameters equal 1, and heavy and fast is where the parameters are 10 to the power 2. Okay, and with that,
Can I just
yeah,
so
of course.
your absence of the half is the ratio, both the Earth is or the other way around.
So,
It's a ratio length scale.
which,
In terms of
sorry,
A divided by LD or LD over.
sorry, which parameter? Yeah, yeah, I'm
before, but I forgot. Here it is.
I'm happy that you asked this question.
All right, so it's basically radius of Earth. Imagine that happens.
Yeah, but I think my point is, and maybe I'll get to it in the end of the talk, I have an extra slide, but I think it's counterproductive to try and reason about the meaning of epsilon based on the constituent parameters, because here is the case where you need to define what's your capital U and capital L. Depending on your capital U and capital L, epsilon can be the Rossby number, it can be the Froude number. And so my point is that the way of looking at epsilon is the where it appears in the equation, which in this case, under this scaling, it's in front of the Coriolis term, so it's a non. I'm saying. Mm-hmm. Okay. Mm-hmm. Mm-hmm. No, Gill, in the 1980 work, used this scaling up to a square root of 2, where the length scale is Rossby deformation radius and the time scale is the Rossby deformation time. He didn't have aspect ratio. No, Gill didn't have an aspect ratio. It's a key point. Well, okay, you can, I mean, I understand that, considering the, no, I don't know, that's a key question which was, I'm prepared to answer. I have an extra slide also. So let's look at some representative solutions. There is a lot going on here, and so I'll guide you through. So the different rows correspond to the 9 samples we have, where the damping coefficient is on the left here, and the rotation rate is on the right here. The different columns are the forcing, geopotential, zonal wind, meridional wind, divergence, and vorticity. And I'm going to make 4 observations. The first simplest observation is the fact that we indeed get the 2 solution regimes. Here is the equatorial solution regime and the global solution regime, and the equatorial is indeed realized for fast rotation. Next is the fact that in the second row for moderate damping and fast rotation under our scaling, we converge to Matsuno solution. So here I'm showing a zoom in on the second row where the shading correspond to our numerical solution and the contours are Matsuno solutions. And you can see that they fit really well. And I should say that this was done very much by construction. We worked very hard to converge to Matsuno solution in at least one case, but you can see that in all other cases, we get considerably different solutions from Matsuno solutions. Next, we can see that for heavy damping, slow rotation, heavy damping, moderate rotation, and to a lesser extent, heavy damping and fast rotation, we have what we call a radiative relaxation, where the forcing is nearly balanced by the dissipation term in the continuity equation, and consequently the divergence is small. So recall that my heavy damping cases correspond to a damping coefficient of 10 to the power 2. So considering that 10 to the power 2 times the geopotential here is roughly 1, which roughly balances the forcing, and the divergence is indeed about 300 times smaller compared to those two terms. And likewise here, and to a lesser extent here. Next, we have a geostrophic balance. So for light damping and moderate rotation, light damping and fast rotation, and to a lesser extent, moderate damping and fast rotation. We have a geostrophic balance when the dissipation term is negligible compared to the other terms in the equations. So in the momentum equations, we get a geostrophic balance indeed, and in the continuity equation, we get the divergence balances the forcing, and indeed you can see that in this case, the divergence is exactly equal to the forcing. Likewise here, and to a lesser extent here. And you can ask, how is a geostrophic balance even possible on a global scale where on the equator the Coriolis term is 0? And the answer is that for a geopotential which is different from for a wave number greater than 0, the geopotential must also vanish along the equator, which is indeed what we see here, and to a lesser extent here. So this case will be in geostrophic balance only outside the equator. And the key point here is that all other cases are qualitatively different or far from geostrophic in that sense. And with that, let's now look at some simple approximations. So far, the last figure was just numerical solutions in general cases. And for that, I'm going to consider the following relative error metric, where XR is the reference or numerical solution in our case, XA is any of the approximate solutions, and importantly, X here is a solution vector, so this would measure the accuracy in the solution as a whole. So starting with the geostrophic approximation, again, in this case, the dissipation terms were found to be negligible. So here I'm showing our relative error metric as a function, again, of the lambda number and dissipation. And it's in log scales, or more negative or smaller values or darker shades correspond to better agreement. So you can see that the geostrophic approximation become accurate in this region, as we have observed earlier. The white line here is correspond to a value of the error of 0.1, which we subjectively decided was where the solutions are Yes. Okay. Yes. So that a value of -1 would be a 0.1. So here you can see the response in these three cases from top to bottom. So indeed, for instance, in the middle one, where the white line just crosses this sample, we still do pretty well. But then outside the white line, it's meaningless. And then the geostrophic balance also corresponds to a zero-order approximation in powers of gamma. And so we can add the next order. And when we do that, we indeed get the accuracy improves, but only within the regions we identified in the zero-order approximation. And that's because outside those regions, the solutions were, as I showed earlier, far from geostrophic. And that's a key point, because we tend to think of motions on Earth as being in geostrophic balance, but in terms of the gamma epsilon plane, I like to say in a non-formal way that it's only about 2 out of 9 of the plane. Next, we have a non-rotating approximation where the Coriolis terms are negligible. And these cases are most accurate here. And this corresponds to, and this is, by the way, solved analytically. It turns out that the system can be reduced to a inhomogeneous Helmholtz equation in the geopotential, which is solved analytically. And I forgot to mention that the geostrophic balance is also analytic. And this corresponds to a zero-order approximation in powers of epsilon half. And we can look at the next order correction. And indeed, the accuracy is improved, but only within the regions identified in the zero-order approximation. We also have what we call the radiative relaxation approximation, where the divergence is negligible, and this is also solved analytically because, for instance, here, for a gamma different from 0, phi is just minus q over gamma, and you can then plug it here and find un and v. And this is the beta plane approximation, which turns out to be the most complicated one, but still analytic. The way in which the shallow water equations, or the shallow water equations on the infinite equatorial beta plane approximate the shallow water equations on the sphere to 0 orders in powers of -1/4. But in order to make that true, the coordinates also need to scale with epsilon. And these equations are well known to be reducible to a time-independent Schrodinger equation of a quantum harmonic oscillator, which is well known and is a nice solution. And indeed, it converges to the numeric solutions for the fast rotation cases shown here. And finally, you may have seen that the geostrophic and non-rotating approximation lose accuracy in this region, and that's because the limit of 0 epsilon and 0 gamma is a singular limit. The equations become underdetermined there. And the only way we found to handle that is using the weak temperature gradient approximation, which was considered by Bressenton and Sobel, where essentially the dissipation term is negligible only in the continuity equation. And it does indeed provide accurate solutions in this region, but it doesn't provide any analytic simplification, so we can only solve it numerically. And finally, it also, it's the best approximation in the region of moderate damping and moderate rotation. And I hope that you notice that the different approximations improve as we go to the edges of the parameter, the region of the parameter plane shown here. So essentially, I'm saying that I think we spanned the plane pretty well. This is just to show that in the case of the moderate damping and moderate rotation, indeed the weak temperature gradient approximation in this case is good. Okay. So here we try to look at which approximation is best. So essentially at each point of the gamma epsilon plane, we look for which approximation the relative error is the smallest, provided also that it's greater or smaller than 0.1 to make sure that it's a good approximation. And we also use this figure to say something about the applicability of our results to nature, namely Earth, Venus, and Titan. So the dashed rectangle here corresponds to the region of the parameter space corresponding to Earth's troposphere. This would be Earth's stratosphere. The oceans, here the dashed rectangle is Venus, and here the solid rectangle is Titan. And fortunately, I don't have time to go over the choices, but I will say that because of the log scales on the axis, factors of 2 here don't change the regions much. And there are caveats to this figure, mostly the fact that, or not mostly, first the fact that our definition, subjective definition of acceptable solution is subjective, so the white regions here can be a little smaller or larger, depending on your requirements. And but also an additional caveat here is the fact that the definition of the most accurate or the most accurate approximation may not be the most appropriate one. And by that I mean that we did consider the geostrophic approximation, but you can see that it doesn't appear here. It turns out that the weak temperature gradient approximation is more accurate than the geostrophic one, but the geostrophic one was simple. So maybe it would be. Sorry? Mm-hmm. Mm-hmm. Yes, that's what I think. And that brings me to the key takeaways here, which is for the most of the gamma epsilon plane, unless you're unfortunate to be in the white area, like in Venus, there is no need to solve the full Matsuno-Gill model. You can get away with some sort of approximation. On the other hand, interestingly, in Earth's troposphere, you will need to involve different approximation or the full model. So you won't be able to get away with just the beta plane. For all practical matters, the Earth's oceans can be described with the original Matsuno-Gill model for all practical matters. Okay, now, as I mentioned, a key result of Gill's analysis was the decomposition to the constituent waves. So here we do a similar analysis, but numerically, we look at the projections of the Matsuno-Gill model solutions denoted here by X gamma on the solutions of the free shallow water equations denoted by X omega. And there are a few observations here. The first one is that in the case of moderate damping and fast rotation, so this table shows the projections on the 9 quote-unquote lowest mode waves, free waves. So the solution in this case consists solely of a Kelvin and a Rossby wave, which together sum up to 100%. And recall that this case was where we found, or by construction, we converged to the Matsuno-Gill model. And indeed, this is consistent with Gill findings, where the solution was just a Kelvin and a Rossby one wave. Next, in the equatorial cases corresponding to the beta plane, Matsuno actually noted that the response to a Kelvin wave can consist only of an EIG wave 1, a Kelvin wave, a Rossby wave, and a westward IG wave 1. And indeed, we see that in those cases, those four always sum up to 100%, but with different fractions depending on the damping ratio, damping rate as well. Next, we have the heavy damping slow rotation and heavy damping moderate rotation cases, where we observed the non-rotating approximation applied. And in a non-rotating case, you don't have Rossby waves. You only have two oppositely propagating gravity waves, which would project on, in this case, the Kelvin wave and the westward inertia gravity wave. And the two actually almost sum up to 100%. And finally, the singular limit and the moderate damping and moderate rotation. In those cases, the solution or this series converges slower. The contributions of the waves shown here sum up to only, this is 70, I don't see what's written there, 83%. How much time do you have? Yeah, okay. I don't know. I only need 2 more minutes. Okay, so up till now, we've considered the solutions for a single Fourier mode, like Matsuno did. But as I mentioned, Gill looked at a finitely supported solution in the zonal direction. And so here we are trying to reproduce the Gill solution as well. And it's easy. Once you have the solution per Fourier mode, you just need to decompose the forcing to those Fourier, or do a Fourier decomposition of the forcing, which is done analytically here. And when you do that, you sum Matsuno solutions appropriately. And indeed, we identify Gill's pattern. This would be the geopotential compared to this, and this would be the divergence compared to this. Yes. There are some differences because it's the zonal domain is still periodic and not infinitely long, and but we do get Gill's pattern. Okay, and finally, this is my last slide. I didn't want to do a summary. I wanted to end on a thought-provoking note, which is the following. Oops, I don't remember what idiosyncrasy led us to call this the radiative relaxation approximation, but in fact, it's also the non-divergent approximation. And so what we find in our result is the fact that there is no overlap between the non-divergent solutions and the geostrophic solutions. And that's it.